Okay, so the idea here is we want to take a sphere and we want to slice it through somewhere, uh, some plane along our sphere. Okay, so that okay, we get this spherical cap, if you will. Spherical cap, if you will. Now, this spherical cap is going to have some radius. I don't know what the radius is. Okay, I don't know what the radius is. Okay, I really don't know because I've sliced it. I know the radius down here is a radius r. But now I'm slicing out some piece here, just coming down a height h, right, and slicing it off. So that I'm just dealing with this piece here, and this is the piece I want to know the volume of. So to be able to talk about this, the first thing we need to do is think about how could we do that so that I'm just looking at that piece. What if I wanted to do the volume of that thing, right? That spherical cap that I'm slicing off the top of my sphere. Okay, what solid would I look at? What solid would I look at to generate that? Well, it turns out the simplest solid we can look at, simplest way to generate a sphere is to take a semicircle, and the semicircle would revolve about the x-axis. And so if we have a semicircle running from minus a to a, and of course if you revolve that about the x-axis, then that would generate a sphere. And now my picture's not perfectly to scale. And then we're slicing off a piece here at some distance h from A. Right? Some distance h from the top here, A. So that's going to make this point be A minus h. And so it turns out then this is the piece that we're actually revolving to generate our spherical cap. It's going to be the integral from A minus h to A, so that we only get this little piece. And for this one, we look at the equation of our curve, which would be a circle of radius A centered at the origin. Well, if we take a circle of radius A centered at the origin, again, we're actually only dealing with the top half of it. So the equation originally would be x squared plus y squared equals a squared, so that y is equal to the square root of a squared minus x squared, or a squared minus x squared to the 1/2. So that's actually going to be our function, and again, that will give this region when we do it from a minus h to a. And so dealing with this thing, we're going to need to compute its derivative, because we need the derivative inside the arc length, which is part of the surface area, which again is actually 2 pi times the function value times the arc length. Okay, so let's compute the derivative here, and then we can figure out the surface area of this spherical cap. Spherical cap. Okay. All right. So y prime by the chain rule, that stuff is to the 1/2, so it'd be 1/2 that stuff to the minus 1/2 times the derivative of a squared minus x squared. Remember, a squared is a constant, so its derivative is 0, but the derivative of minus x squared is minus 2x. So simplifying, we get y prime is equal to minus x over the square root of a squared minus x squared. Okay, So now we're ready to take a look at our surface area. Surface area is going to be, again, the integral in this case from a minus h to a minus h to a, of 2 pi times our function, square root of a squared minus x squared times the square root of 1 plus my derivative squared. Right, and then dx. Okay, so what remains here now is to simplify and get this stuff cleaned up. Okay, well, first of all, we're squaring it, so the negative will go away, and that'll just become x squared. In the bottom, we'll just have the square root squared, so that'll just be a squared minus x squared. So we would need a common denominator over that a squared minus x squared. So the 1 over there would just be, in the numerator, a squared minus x squared. And then plus the x squared that's there. So it turns out the x squareds cancel out, and we get a squared over a squared minus x squared. Now all of that stuff is inside the second square root there. Is inside the second square root there. So bring my 2 pi out front, 2 pi integral from a minus h to a of square root of a squared minus x squared times, and again the second square root is going to distribute, so I'm going to have square root of a squared over square root of a squared minus x squared dx. So that means the square root of a squared minus x squared cancels with the square root of a squared minus x squared, and we just have the integral 2 pi integral from a minus h to a of a dx. Now remember, a is a constant. We're integrating this thing with respect to x, and the x variable has left the building. So the integral at constant is just going to be 2 pi a x, evaluate it between a minus h and a. And then we just work that out and see what it gives us. 2 pi a times a minus 2 pi a times a minus h. Well, look what's going to happen here when you distribute. That 2 pi a is going to be minus 2 pi a. So all that stuff should go away. And so we're just really going to have minus 2 pi a times h. So it turns out that the surface area of that cap will be 2 pi a times h. 2 pi a times h. Okay. 2 pi a times h. And if it turns out you decide you want your spherical cap, to be the whole sphere, then let h be 2a. Right? That way h has been marked down here at 2a. And if you put 2a in for h, then you'll get 4 pi a squared, which is actually, if you look it up, the surface area formula for a sphere of radius a. It'll be 4 pi a squared. So this does agree with the surface area for that as well. So this is a pretty cool formula here. 2 pi ah will be the surface area of the spherical cap that you chop off.